All right, so what about this reaction? So I have a reaction up here. It shows that it's maybe forming that and that. But a minute ago we said that, so I guess to rephrase, the reaction below produces product. So it says question mark, right? So how could this be? Can this produce reaction product by an SN2 reaction? So think about that with what we've talked about so far. Could this reaction be forming this by an SN2 mechanism? All right, a lot of you are looking a little bit confused out there. Well, what makes reaction rates of SN2 speed up? Stronger nucleophile. This is probably a pretty strong nucleophile. It's negatively charged. What about good leaving group? We do have a good leaving group. But what's the other thing? The substitution. So this is a tertiary alkyl halide. Tertiary alkyl halide. And what we said about those was that essentially the nucleophile, because there's these big CH3 groups all right around that little sigma star orbital on the other side, that the nucleophile essentially can't reach back there. So essentially, this cannot be occurring by an SN2 reaction if we are forming product. It must somehow be happening by a different mechanism. So can this be an SN2 reaction? We'll just say no. Tertiary alkyl halide, so nucleophile can't reach, we'll just say reach sigma star, can't reach that anti-bonding orbital. So if that's the case, then it must not be a standard SN2 mechanism. So let's check some rate data on it. So if the initial rate was 1, we can see what's important in the rate determining step by changing the reactant concentrations. And it turns out that when we double the concentration of this, we actually get a doubling of the rate. The rate equals 2. So we went from 1 to 2. So this must be involved in the rate determining step. Well, what happens if we're doubling that? We're leaving that as beginning concentration. So it's the same concentration that we had here, and it turns out that when we double the concentration of this azide, or of this N3 molecule, it's called an azide, we actually get no impact on the rate. So somehow this reaction mechanism has changed based on this tertiary alkyl halide, where the rate, what is it equal to? So take a minute, pause the video, come back once you're done, after you've decided what the rate equation is. You did that, you're back. The rate equation equals the rate constant K, and only multiplied by the reagents that are involved in the rate determining step. Not involved in the rate determining step. The only thing that's involved in the rate determining step that we know about is the alkyl iodide. So it turns out that this is what we call an SN1 mechanism. This is an SN1 mechanism. So the SN is the same as what we saw for SN2, substitution, nucleophilic. This is a nucleophile. We are doing a substitution, but the 1 equals unimolecular. So that's the big difference compared to an SN2 reaction. SN2 was bimolecular. This is unimolecular. So more on that in a minute. All right, so how can this mechanism occur? How can we replace this iodide with the N3 if it's not happening all at the same time? Well, it must be a stepwise mechanism, right? Instead of the bonds forming and breaking at the same time, we must form a bond, then break a bond, or break a bond, then form a bond. So we kind of have two options, right? We could form, then break. So if we tried to, so one option would be form, then break. So let's try that. So if we form the bond first, then this N3 would somehow attach there. That's our form. and then we break. So then we'd have step 2, which is the breaking step. So this is a stepwise mechanism. Those arrows do get us to the product. Is this likely? What do you guys think? Oh, yeah, I see some of you in the back are scratching your heads. This doesn't make a lot of sense. What's wrong here? Exactly. This is a Texas carbon, right? This carbon has 5 bonds. That's way too many. It can only have 4 bonds. So if this was the mechanism, the energy of activation would be so high that it would be impossible for this to happen. This is crap. I'll come back. All right, so we just saw that forming the bond before breaking the bond makes no sense. So let's try the other. Break, then form. That's the only other way that this could happen. So in this way, we would break our carbon iodide bond. That would produce, so this is step 1. Step 1. That would produce this carbocation intermediate, because the carbon there lost a bond. We would have I minus, and then we also have N3 minus. So all of that stuff is floating around in solution. At this point, N3 minus is attracted to that carbocation. So, and also this carbocation is now sp. What's the hybridization of this carbon? Good job. It's sp2 hybridized. So instead of the N3 needing to get to that really small antibonding orbital, it now is adding, so if it's sp2, that means it's trigonal planar. So I'm going to kind of turn this, I'm going to turn it sideways for us, because essentially we have an empty p orbital here. So what does that look like? If we turn this sideways, so we're just redrawing this carbocation, it would look like this. And instead of having a tiny p orbital, or sorry, tiny antibonding orbital, we have this big empty p orbital where the nitrogen can add to either that lobe of the orbital or that lobe of the orbital. The positive isn't on that side. It's in both, right? It's everywhere, but I don't want to write 2 positives because then it would imply that there were 2 positive charges in that orbital, but there's just 1, but it's shared between both sides. So anyway, it was really hard for N3 to get to the back of that, but because this is so big and open, it's now very easy for the nitrogen, for the N3, for the nucleophile to get to that orbital. So this was step 1. Step 2 makes that final bond. Step 2, we've formed that bond. So essentially we have a 2-step reaction, and we should draw a reaction coordinate diagram to show those steps. What's the rate determining step going to be? What's the step that is going to be most unfavorable? So think about that, pause that, draw your reaction coordinate diagram, and then come back. Okay, you did that, good job. So is the first step going to be unfavorable or the second step? Well, what takes energy? It takes energy to break bonds, and we broke bonds in this first step. So this, it turns out, is the rate determining step because it took energy to do that. So essentially, we have our starting materials right here. We went up to our intermediates. Our intermediates are lacking bonds, so it's higher in energy. And then getting from our intermediates to our product, we went there. And again, you would have needed me to tell you this part. This was an exothermic reaction. So the products are more stable than the reactants. So that's what that looks like. So compared to a SN2 reaction, that's a single step. This is a multi-step reaction. Yeah, so that's kind of the basics of an SN1 reaction, how it happens, what happens. We'll talk more about that soon.